Alright, so today we're looking at a few different ones: circles, ellipses and hyperbola, which we've done before. So circles first up. So the Cartesian equation for circles is there are other ways you can write it. So here we've got a Cartesian equation, so a circle of radius r and the centre at h and k. The Cartesian equation is x minus h not k, x minus h squared plus y minus k squared equals the radius squared. And so if we were to sketch, so this one for example, x plus 2 squared plus y minus 5 squared equals 4. Excuse me. A couple of different ways, but first of all we need to identify where the centre is, and the centre would be at -2 and 5, and our radius would be 2. So then there's a couple of different ways that you can sketch. You can find intercepts and things like that. You need to be guided by the question and how they write the question as to what you need. But the simplest way to sketch is this way. And it's not going to end up looking very nice if I use that scale. So one way you can look at sketching this is find your centre. And the centre is at -2 and 5, which is there. And then because the radius is 2, you can go 2 in any direction, so horizontally and vertically. If we go to the right 1, 2, so the point would be there. We go to the left 1, 2, goes through that point. If we go up 1, 2, goes through there. And if we go down 1, 2, goes through there. And then we can join it up, and there's a nice circle. Alright, but as I said, you need to be, whether you need intercepts and other stuff, you need to be guided by the question and how they're asking the question.
So you don't need to put the intercepts in?
Well, what you need for any graph is you need some significant points so that we know whereabouts the graph goes. So with this, because we know that's the centre at -2 and 5, and the radius is 2, then we know that this point here would be -4 and 5. We know that this point here would be -2 and 7. that's our y-intercept, so 0 and 5, and this one here, -2 and 3. All right, so we've got 4 points there that we know that our circle goes through. All right, but if the question specifically said by finding the intercepts, then you need to find the intercepts. But, you know, for all graphs, when we're sketching, we're not plotting, we're sketching. When we're sketching, we need some points to guide us as to whereabouts it will be. All right, now sometimes, because we're in Spesh, they complicate the way the equation looks. So sometimes it might not look nice in this form here. It might be expanded or something like that, and then we need to adjust that into this form. So sometimes the equation is not in the form we want. And what we would do for this particular, for circles, because these brackets are perfect squares, so we need to complete the square to get some perfect squares. Alright, so let's do an example. So, e.g. Alright, so this is not in the form that we want. We need those, those brackets which are squared, so then we can find out our centre, and then we can find out our radius. So we need to complete the square. So what we do is we group our x bits together and our y bits together, and leave the number bit out over there. And then we'll go, alright, so we'll complete the square. So to complete the square with the x's, what would that bracket be? X plus 2. Now, when we expand that bracket, there would be a number on the end here, 4, and because I've now added an extra 4, I need to keep it balanced and take 4 out over there. Then with the y part, that bracket would be y plus 3. And again, when we expand that, we would get 9 here. And so we take 9 away from over there. So minus 12 minus 4 is minus 16, minus 9 is minus 25, equals 0. And now we would get our radius, what do we need to do with that 25? Plus it over to the other side, so we now have got it in the form that looks like a circle. And so where's our centre? -2, -3, and our radius is equals 5, and so when we sketch it, -2, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So again, if we use the same strategy we used before, go to our centre, -2 and -3. There it is there. We've got a radius of 5. Horizontally, move each way 5 from our centre, vertically the same. Moving 5, so we've got a point over there. -7 down there. -3, that's up here at 2. -8. There it is. So clearly there's some x and some y intercepts there. And as I said before, be guided by the question as to whether you need to find them, because often they'll have, roots and things like that. Often they're not going to work out as necessarily nice numbers. All right. Anything else about circles before we move on? Alright, so the next one is ellipses. So an ellipse is a squashed circle. And the Cartesian equation, because there's other equations, is this form. Alright, so there's some similarities here between our ellipse and our circle. Alright, so they've both got these perfect square brackets. Here we've got a minus instead of a plus. And we've got a 1 over here, but then we've got some numbers over there. These numbers are different. So this represents an ellipse, and so if you like we call it the centre. Alright, so where we're working from. Same here with our translations, H and K. And then we've got these other two numbers, the A and the B. And they contribute to what's called the semi-minor and the semi-major axes. So our ellipse is like that. Alright, so and then the centre of it will be there, and then we go each way a certain amount. each way that we go, that certain amount for in the x direction, it's this a that will go each way. And in the y direction, we would go a certain amount. And the amount we go is this b. So as you can see, depends how stretched horizontally and vertically it is, and so that's what we're calling our semi-minor and our semi-major axes. Alright, it's not critical about which one you call a semi-minor and which one you call a semi-major. That bit's not critical. But what the critical bit is how far you've gone from this centre point. Alright, so often we call a semi-major axis in the x direction and a semi-minor in the y direction. The semi-major axis, and we go A units each way from the centre. In the x direction. And our semi-minor axis we go B units each way. In the y direction. So if I do a rough sketch here, for example, if we've got a point H and K, then horizontally I'll go across the distance of A further across here, distance of A that way, should be H minus A. And then vertically, I would go up to here, and so I'll go B up in the y direction, or I come down B in the y direction. There's my beautiful ellipse. Looks much better in my notes because I used my mathematics.
What happens if you draw if you got an ellipse that has like different A values in each? Or is that not an ellipse?
That's not
Like
an ellipse.
one.
So for your ellipse, you have to go, this distance is the same.
Yeah.
This
But
distance
what if like
is the same.
you went 2 units right and then 3 units left? That's not an ellipse. What's that?
Don't know, have to have a look and see. Yeah.
Right.
But no, that's not an ellipse. You have to go the same amount each way.
Cool.
And it doesn't matter. I mean, here I've drawn it where the size of A is bigger than the size of B, but it could be the other way around, and it's long here and narrow there. It's still an ellipse. All right, so let's sketch one. Alright, so we need to know where that centre point is, and then we need to know how much to go this way and how much to go this way. So centre point for this one would be 2 and 3. A, 3, don't forget you've got to square root that number there, 3. And B, 4. Okay, so the simple way for us to sketch is this. So start at your centre, which is at 2 and 3. And then, knowing our semi-minor and our semi-major axes. So the A is 3, so we go 3 each way from the centre in the x direction. So if that was 2 and 3, it's now going to bring us out to 5 and 3. When we go to the right, when we come to the left, we're going to be back here at -1 and 3. And then we're going 4 the other way. 1, 2, 3, 4 up, which is then 2 and 7. 4 down, which is 2 and -1. And then we end up with beautiful ellipse like that. Right. Any more there? From anyone? Yes? No? Maybe? No? You know what? I made a mistake. It's still a plus. Change all of those. And people in YouTube world, should be a plus here. What I was thinking. Go and change all of those. Getting ahead of myself. Getting ahead of myself. The next one's where we've got the minus in here. Old age, it is. Old age. Alright, so I better just write that fix it up. YouTube people, all my 3 followers. It's x minus h squared over a squared plus y minus k squared over b squared. For our ellipse. If these two are the same, it's a circle, so it's got to be a plus there, doesn't it? Terrible. Now, if it was a minus in there, it gives you a different graph. And that graph is what's known as a hyperbola. Now, we have done some hyperbola before. The hyperbola that we have done before is rectangular hyperbola. Well, in methods, that's what you do anyway. So in methods we do rectangular hyperbola, and rectangular hyperbola are of the form 1 on x, and our rectangular hyperbola are there like that. So these hyperbola that we're looking at here with this equation, they have this, still have this curvy bit, but the asymptotes of them are not vertical and horizontal. So here is the Cartesian equation. So it's very similar to the ellipse. But it's got a minus in the middle, not a plus. All right, so key things is that we have a centre, and the centre is again H and K. We have some vertices, so if you like to think the point that's closest to the origin here, that point there, that's closest, that would be what the vertices are. So the vertices are the points that are closest to this centre. And they are plus or minus A, so you start at U and K. Now also, remember from our rectangular hyperbola, we've done methods, we've got some asymptotes. So if these things are hyperbola as well, then they would have some asymptotes. And their asymptotes, the equations of them are this. B on A is the gradient of it, x minus h plus k. Now, there would be two of them, not just one of them. So to get both of them, it's plus or minus there. So one of them is the positive gradient, the other is the negative gradient. And both of them, our asymptotes, will intersect at the centre. Alright, so I'll just write that. The asymptotes intersect at the centre. Alright. Let's do an example, shall we? You got that? Can I rubble that? Alright, so let's sketch. Alright, centre. Where's the centre?
1 minus
1 and negative 2. A, 2, B, 3. So, vertices. So vertices is h plus or minus a and k, which when we put those numbers in, it's 1 plus or minus 2 and negative 2. So that means we get 2 vertices. One plus 2 is 1 minus 2 is negative 1. There's our 2 vertices. Asymptotes. So our asymptotes is y equals plus or minus b on a, x minus h plus k. So if we put in our numbers, it's y equals plus or minus b on a, so 3 over 2, x minus 1 plus k, and k is negative 2, so minus 2. Now you could expand, collect your like terms and stuff like that if you want. Right. I'll show you another way that we can do it. If you do, and I've prepared it earlier, if you expand and collect your like terms, one of them becomes and the other one becomes that. But you don't need to sketch it, you don't need to expand those and collect your like terms. And I'll show you now how we can do that without expanding and collecting our like terms.
Is that 3 on 2x minus 7?
Over 2. Ready for me to work through how we sketch this? Yes, no, yes. Alright, so let's mark in some stuff. So first of all, let's mark in the centre. So the centre is at 1 and negative 2. The centre's here. We've got some vertices. Got 2 of them. One of them is at 3 and negative 2. The other one of them is at negative 1 and negative 2. The other thing we've got is some asymptotes. Alright, so you can have a look at that, and then you can have a look at, see where your y-intercept is. If you expanded, collected your like terms, but you can just work from here. Because we know our asymptotes intersect here at our centre. If we've got a gradient of 3 over 2, a rise of 3 and a run of 2 means we go up 1, 2, 3 and across 1, 2 to there. So this asymptote, which is this one, if I draw it straight instead of curved, oops, it goes like that. And the other one, which has the negative gradient, again we would start here, negative gradient, so we go down 3 and across to there, and so it would go like that. Alright, and as you can see, intercept there, -0.5, intercept there, -7, and on 2, -3.5. Alright, so you can use either of those methods. Expand to collect your like terms, then use your centre and your y-intercepts. Or you can just go from here, from your centre, and use the gradient. So, like other hyperbolas, they curve and head towards our asymptotes. So there's this one here like that, and on this side goes around like that. Alright, so they are hyperbola, Cartesian form. Don't confuse them with the other hyperbola that we've done in methods and that, which are rectangular hyperbola. But you can see the features of both of them are the same. They have asymptotes that cross in the middle, and they curve around towards, just like the rectangular ones do. So that's why they're in that same family, because they have the same behaviour things. All right, anything there that needs clarifying?
Yeah,
Do you have to?
if the question asks.
If the question asks for it, yeah. But again, they're not going to be numbers. They're going to have roots and things like that in them. Yeah, you can find them. I just haven't today. But y equals 0 to find your x-intercepts. This one doesn't have any y-intercepts, but they may have y-intercepts. If it was moved across here a bit more, would have y-intercepts.
So we don't need it on.
Not unless you be specifically asked for them, I wouldn't think, no. Because you've got some key stuff going on here, haven't you? You know, this centre, you know, there's your asymptotes. You know, this is your vertex, so this is, you know, the closest it gets to the centre. And then if the point's here, it's got to curve onto this side. This side of the asymptotes, not the other side. So there's enough information there to know whereabouts it is. But if you're asked to show them, then you need to show them. All right, that's it then. Don't forget, like and subscribe.